In the previous video, we have seen a simple form of a closed-loop system that has a single forward and feedback blocks with the inclusion of a single summing and a single takeoff point. However, when we deal with control systems, then we come across various complex block diagram representation of systems that holds various functional blocks with multiple summing points and multiple takeoff points. As engineers, we tend to simplify dynamic systems by making educated assumptions, aiming at simpler block diagrams. But still we may end up with somehow complicated dynamic representation, as shown here in this example. In this cruise control example, we have limited the disturbances only to two. First is the measurement noise disturbance, which we then also completely ignored for the reasons that we will discuss shortly. And the other disturbance was the slope of the road, which was simplified and was the only disturbance considered. Here, the engine load disturbance represents the slope changes in the road and considered as disturbances that drive the engine output away from its desired behavior. In addition, we have assumed that the disturbance is a low frequency in nature, i.e., the slope changes slowly when you drive along the road. And that's why, in general, some engineers use step signals or ramp signals as prototypes for such disturbances. The second assumption is that we have completely ignored the measurement noise from the sensor or controller. Measurement noise typically has high frequencies. Thus, the average of the noise is typically zero. If this was not the case, the sensor will give very misleading information about the process or the engine, and it would not be possible to control it well. Moreover, we have also ignored the sensor loading and its dynamics, in which, if also exists, could affect the accuracy of the sensor information obtained. For more information on sensors dynamics, review the measurement and instrumentation courses. Now, with all the assumptions we have assumed and those ignored about the car engine, etc., we still can arrive at a block diagram that is not relatively simple or easy to analyze. To analyze such dynamic system in terms of stability and to embark in designing a controller, we need to obtain the characteristic equation. This can be done by reducing the multiple subsystems into a single transfer function, hence the need for the block diagram reduction techniques. Please note that these block diagram manipulations shown here only work if the blocks in question represent linear operations, or your system can be represented entirely in the Z or the S Laplace domain. So one by one we will discuss the various rules that can be applied for simplifying a complex block diagram. Let us start first with the serially connected blocks. When the blocks are connected in series, then the overall transfer function of all the blocks is the multiplication of the transfer function of each separate block in the connection. Suppose we have two blocks in cascade connection as shown here. Consider U as the intermediate variable, then we can say that U equal to X G1 and Y equals U G2. Hence y equals to x times g1, g2. Then we can replace the two blocks with different transfer functions into a single one, having the transfer function equal to the multiplication of each transfer function without altering the output. The second main transformation is when the blocks are connected in parallel. In case the blocks are connected in parallel, then the transfer function of the whole system will be the addition of the transfer function of each block. Suppose that y1 is the output of the first branch and y2 is the output of the second branch. Then y1 equals to x g1 and y2 equals to x g2. Y is the output of y1 plus y2. In this case, we can express y as the summation as follows. Therefore, connected blocks in parallel can be replaced by a single block with a summation of the transfer function of each block. The third main important transformation is eliminating a feedback loop. The proof for this is simple. First, express the output y in terms of the error times g. Then simply find the value or the expression of e in terms of the x and b as shown. Simply replace the value of e into the first expression and rearrange. Kindly note the sign in the denominator of the transfer function. We will have 1 plus gh when bs is subtracted from the input. On the other hand, we will have 1 minus gh if bs is added to the input. The fourth transformation is the intermediate transformation, which is moving a summing point behind the block. Suppose we have a combination where we have a summing point present after the block as shown here. We need to move the summing point behind the position of the block without changing the response. So for this, a block with gain, which is reciprocal of the actual gain, is to be inserted in the configuration in series. The fifth transformation is also an intermediate transformation. Here, we need to move a summing point ahead of a block. Suppose we have the configuration shown here with a summing point and a block. If the summing point is to be moved from a backward position to a forward of the block, in order to keep the output unaltered, we need to add a block having the exact gain as the original one. The sixth intermediate transformation is shifting a takeoff point behind a block. Suppose there is a takeoff point ahead of a block, as shown here, and we would like to move that takeoff point behind the block. We need to keep the output of the branch, which is xg, the same. So with the backward movement, the branch value will become only x. So we have to add another block with the same gain as the original gain. This will make the value of the branch after moving it backward xg, the same as it was before. The seventh intermediate transformation is moving a takeoff point ahead of a block. Suppose we have a combination of a takeoff point and a block as shown here. If we need to shift the takeoff point ahead of the block, then we must keep the branch output as is, which is x. In this case, we have to add a block with a gain which is reciprocal of the gain of the originally present block. The eighth intermediate transformation is the interchange of the summing points. Consider a combination of two summing points directly connected with each other, as shown here. We can use the associative property and can interchange these directly connected summing points without altering the output. A ninth intermediate transformation could be the splitting or combining of summing points. A summing point having 3 inputs, for example, can be split into a configuration having 2 summing points, or 3 summing points can be combined to form a single summing point. These are the block diagram reduction rules that we will be covering for the linear control system course. In the next video, we will apply these rules to a more relatively complex block diagram.